Okay, good morning. I think we are ready to start. That means this is the second session in this week, and I will talk about the next test. Okay? And I did print the summary of all of the tests. Hopefully you remember yesterday I was mentioning about that document. That means this is really important because we have the list of all of the tests that we have to know. Yeah, I just print and I highlight the tests that we cover. That we still have a few tests to talk about. Okay, this is like 2 pages. That means you can see the highlights, which I can quickly go through. The test for divergence, and then the geometric test and the P-series test that we learned yesterday based on the integral test. And we also learned telescopic test. Okay, that's just a little bit of the summary, and I know that this will be helpful. Okay, because I talked to a few students and they really like this summary. You can of course make another summary of the test, but you can use this one. This is section, I believe, 11.7 is the summary. That's you can find that document under that section. Okay, that's what we will do today. We will talk about the comparison test, which theoretically, it's not really new test because talking about the improper integrals, we talked about the comparison, like how we can compare. If the improper integral was divergent, like I always imagine divergence as like infinity, huge, and everything what is beyond, everything what is greater, it's also divergent. Right? That means that, of course, we have to have these 2 expressions, 2 functions, and the relation between these 2 functions. Or if improper integral is convergent, okay, convergent means like a finite number, then everything what is smaller must be convergent too. Okay, that means similar thing we will apply to the infinite series. Okay, let's start. What we have, comparison tests. That means we will take something like that. Okay? The infinite series from 1 to infinity, 1 over 2 to the n plus 1. Okay, and we can definitely say that this reminds us just 1 over 2 to the n. Okay, because this one is nice and easy formula. N is placed in the exponent. That means this is definitely a geometric series. We can see the first term is 1/2, and the common ratio is also 1/2. How can we compute the common ratio? The common ratio is just the entire quantity taken to the power of n, which if I will do this way, I can see right away that it's 1 and 2, 1/2 taken to the power of n. Or we can always, if this is like, if we have also different method to finding the common ratio, we can take the second term and divide by the first one. Or we can take the third term, divide by the second one. 2 consecutive terms when we dividing, because that's the ratio, common ratio. The first term is defined for n1. That means it's half. The second term is defined for n2. That means this will be 1/4. 1/4 dividing by half means multiplying by 2 over 1, which of course is 2. It is half. As we can see, that's the way, or just looking at the formula. Okay, that means the common ratio is 1/2. Then, based on the property, this is convergent, infinite series convergent. Of course, the geometric one. And we can even compute the sum, yes, just in case, if we have to. What formula we have? We have A as a first term, 1 minus the common ratio. A, the first term is 1/2, 1 minus the common ratio. 1 minus 1/2 is 1/2, 1/2 over 1/2, it is 1. Right? That means I just prove that value because I want you to know all of the numbers. Okay, but let's come back to our formula, the original formula that we see. We have something extra. Right? That means this, even if it doesn't really make a big difference, plus 1. Yeah, if we're thinking about the terms going to the infinity, adding plus 1 is not really a significant number. However, it's changing the entire formula. Having that +1, it's not a geometric one, okay? That means what we will do, as I said, this original series reminds us this one, the nice, easy, known one. And what we will do, we will try to compare them. Okay, that means I can just pull out the expressions, the main formulas, and this is my original one, this is my new one that I figure out that I can compare with. And comparing these two fractions, of course, seeing a denominator greater, the whole fraction is smaller. Okay, and then I can also apply this for the summation, for the infinite series. And we know that the sum of this geometric one, it's 1. And then something that is smaller, or I can say everything what is smaller must be convergent. Yeah, we just remember, I just said this based on the section 7.8 improper integrals. That means we will apply exactly the same things. Okay, that means I can say that my original series is convergent. Okay, and I can say by comparison test. Comparison test. And since we directly compare, you can probably see in the textbook, we just saying direct comparison, which we will say direct comparison test. Because we do have another form of this comparison test. Right? That means this one is direct comparison test. Okay, that means that's pretty much everything. Okay, oh yeah, we will practice. But what is the point is, we can see in order to compare with something we did with this one, we have to find this. This is the extra job for us, to find a good, easy formula that I can compare with my given one, which is always a little bit challenge. Okay. And let's see. Oh yeah, I'm trying to explain this. That we do have, if we have convergence for one formula, and then everything what is less, it will be convergent. And I use the geometric one. One important note is, we can use the comparison test only for the series with the positive terms. I will pick the red. Okay. Please remember, when you see like the -1 to the n being like the part of the formula somewhere, like which this means is the alternating series, then we can't really apply the comparison test, because we know having -1 to the n, one term is positive, one term is negative, positive, negative. Of course, we still have to check the partial sum, but this could really like, this is not easy to determine the relation, like greater or smaller, okay? Because we have to know if something is greater or smaller, because if the inequality, if the relation doesn't work, we can't even use comparison. Okay, that means please remember, only if the terms are positive. You can also see this on my summary page. Okay, that means this is simply the comparison. I don't have to even like prove everything, because we did kind of proof yesterday for the integral test, and 2 weeks ago or 3 weeks ago for 7.8 section for the improper integral. That means this is just the test. Okay, suppose that the infinite series a sub n and the b sub n of course are the series with the positive terms. Okay, and then let's see how we can compare. If b sub n is convergent, that means everything what is smaller, yes, we can see smaller, it's also convergent. Or if the series b sub n is divergent, everything what is bigger, greater, it's also divergent. Yeah, like greater than infinity. I don't know if I can say this way, but I kind of like, yeah, I always picture this like this way. Okay, that means that's the way that we can compare. Of course, if the inequalities will be the other way, then we can't really compare. Okay, we can't. Like, let's say let's say we do have B sub n. Oh no, actually A sub n is my original one, B sub n is the new one. And let's say this is divergent, okay? And my infinite series A sub n, it's smaller. That means I don't know if it's smaller, could be convergent or actually could be also divergent. I don't know. We can't use comparison if the relationship, if the inequality, like it's not cooperating, okay? Or the same way for the convergence. If B sub n is convergent, and something that is bigger, and we get the relation this way. The same way, like if this is convergent, something which is big, like the summation is bigger, I don't know, could be huge, could be infinity, or could be still a finite number, could be still convergent. Let me just make sure that we just applying the logic. Okay. What else I have before we start practicing? Okay, that means this is some information, some hint maybe, like how to use the comparison test, what to compare with the original formula. If we have a ratio of two polynomials, right, it's always nice to keep, actually, it's kind of like the first one and the third one is almost the same, first one and the third one. Because what I can do, having the ratio of two polynomials, like a rational function, I can keep the highest power of the numerator and denominator. And then I can simplify, and probably simplifying, I will end up having my 1 over n to the power of p formula. And then this is p series, and we know the condition for convergence or divergence. Okay? Or, like I did my first example, we can always try to look for the geometric property. Yeah, we can like get rid of some additional numbers, focus on the main, like the main formula for the geometric one, and also we will know if it's convergent or divergent almost right away. Right? I mean, this is just an example, but maybe solving some problems like we will do today, you will get an idea what to compare with. Okay, that means, for example, this one. Determine whether the given series converges or diverges. 5 over 2n squared plus 4n plus 3. Okay, that means what I will do, as I said, I will take my I will take my original formula, and I have no option, I have to keep the 5 on the top, but in the denominator, I will only keep the highest power. Because always at infinity, we remember limits at infinity, always the leading function is important. That means that's what I'm doing. And now let's see, a relationship is important. I can definitely see that my fraction on the left-hand side has bigger denominator, then the whole fraction is smaller. And then I can put 5 over 2, because it's just a constant, in front of the sigma, and my main formula is 1 over n squared. Okay, do you see? That's what I said. Having a polynomial, taking a leading function, and then rewriting, simplifying, I end up with my p series test. And then we can definitely see that p-value is 2, greater than 1. This infinite series is convergent. Convergent. And now, okay, the first question today. Do you think I can conclude convergence of my original one? Can I say that this is convergent too? Can you type your answer, possibly? Because we still have the same. I could put my sigma right away. Yeah, that means if this summation is convergent, this means the finite number exists as a sum, then something that is smaller is going to be convergent or not? It is convergent, yes, thank you, Roger. That means this is definitely convergent. That means I can say this converges, and as I said, the test is important. direct comparison test. Okay, I use and always when we actually using the comparison test, we have to say, oh, I don't want to forget, converges by direct comparison test, and we comparing with, of course, with this one. Okay? Because we may have I mean, we have to find what we're comparing with. Everything has to be correct. That means it's always important to point, to show what we're comparing with. Okay, but we can see what I did. I took, because that I can circle maybe blue. Yeah, that's the thing that I did. Okay, let's look at my next example. Okay, that means this is the note. Because do you remember from yesterday, like in order to use the integral test, a function must be decreasing. And we may have a situation that is decreasing, not exactly from 1 or 2 or 3, like we may have the decreasing condition like later on. That means when we skipped a few finite numbers, it's still fine. That means even if we're making some comparison and the comparison doesn't work, okay, for a few numbers, like for example, I can maybe show you n, and this will be, we may have a function natural log of n. Okay, oh, actually this one works good, but I can still, because that's what I always compare. And this will be just n. That we can definitely see that ln of n is definitely smaller than n. Yeah, that means this is like one thing that we can compare. We can like remove natural log of n and we can put n. Oh, I should actually put the dots, right? Because we talking about the sequence. We will add the dots. This is just the, okay. That means that's actually one thing that I always try to use, because n is much, much simple in the formula rather than natural log of n. That means you may remember this. Or I also like, well, I just wanted a nice, this is just one, just simply the horizontal line 1. And we know that we, ln of e, right? Ln of, if this is e, ln of e is 1. Okay, that means I'm good. That we can see this situation. Definitely function natural log of n, it's greater than 1, but starting from 3. Yes, we remember that's the, I can say 3 because we need a positive integer. And that's me, for example, this one. Like we can see, don't worry for the few numbers before, because the logarithmic function is actually lower than 1, but we're really looking at infinity. That means that's another comparison. Instead of ln of n, we can maybe put 1. But yeah, you can see this is the relation. Instead of ln of n, we can put n, but then the relation is this way. Yeah, that means some ideas. But don't worry if few finite numbers are like simply not included. Okay. Oh, okay. Oh, I didn't want you to see this, but okay. Let's see. That's what we have. We have an infinite series from 1 to infinity, ln of n over n. Do you remember yesterday what test we apply? Who can type the test for me? Do you remember what we did yesterday? It was exactly the same formula, ln of n over n, because it's relatively easy to integrate. That means if the formula is easy to integrate, you can always try integral test, and function is like positive, continuous, and decreasing. We proved that. But if you check the slides from yesterday, integral test is a little bit time consuming. Yeah, that means what we can do now, we can try to compare. I took my original formula, ln of n over n, and just what I did, I copy n, but ln of n, I compare with 1. Yes, ln of n and 1. And we know that this is greater, of course, starting from 3. Okay. Let me actually even I can even change this one, doesn't matter. Okay, and now on my right-hand side, okay, let's just quickly analyze the relation. If the denominators are the same and the numerators are different, yeah, that we're looking which one is bigger, then the whole fraction is bigger. And of course, natural log of n is greater than 1, then the whole fraction is greater. Okay, and then I can even start from 3. Natural log of n over n, the same relation, and we recognize this one. Yeah, it's really nice, beautiful, infinite series. It's the harmonic one. Harmonic series, if you remember from section 11.2. Okay, and harmonic series, can you just confirm it is convergent or divergent? Oh, yes, thank you, divergent. Okay, of course, I can also say is the p-value 1, yeah, it's the p-series, I can also say by the p-series is divergent. Because it's 1, it's exactly 1 if it's 1. That's the same thing, but for this one, 1 over n is we just call harmonic. And you can check the section 11.2. Okay, that's me. Now let's come back to our comparison. My original formula, it's actually, that's the question. Can I conclude divergence based on this relation? I have something that is huge, divergent, right? Divergent, and something that is bigger. It's also divergent? Can you just confirm for me? Of course it is. Thank you for typing. That means this is definitely divergent. And now please be really careful. Again, I'm writing by direct comparison test. Because what is the easiest mistake is to say, oh, this is divergent by harmonic series, or this is divergent by p-series test. No. We're comparing with this, right? And of course, we're comparing with 1 over n, which is harmonic, or, yeah, but my original problem is divergent by direct comparison test. Okay? Remember that will be the option if you see the multiple choice question. Okay? Not because I can type like, oh, divergent by because it's harmonic, divergent by the p-series test. No. Or divergent by, oh, I can say divergent by integral. That's actually correct, yes, but that I will not. That's the topic from yesterday. Because we may use different tests, yeah, depends. That means also it's true statement if it's divergent by integral test. We did this yesterday. Okay. What is my other notes? Okay, that means this one is I just typed this, what I said, that if we have not good relation, the inequality is not in the good direction, then we can't really conclude divergence or convergence. Then the comparison test, we can't apply, okay? We have to make sure that we know that. Okay, that means, for instance, let's consider something like that. Infinite series from 1 to infinity, the summation 1 over 2 to the n minus 1. Okay, that's what we can see. We can still probably pull out just the main. This is leading and this is leading. That's what we did at the beginning. And this is definitely the geometric one. The common ratio is 1/2, less than 1. It's convergent. Okay, infinite series convergent. Okay, and then I'm definitely comparing, because that's probably the only formula that I can compare. The easy formula, because theoretically you can compare with anything. but we have to make like some good comparison, good conclusion. That means this is the only good formula at the moment to compare with. But now let's see what's the problem. The problem is I'm not adding one like it was on my first example. I'm subtracting. That means making a denominator smaller, the whole fraction is bigger. And now I do have a problem. Oh, okay, we can see this because I can't really compare. Let me just write, because let me put here. This is convergent, and something that is bigger, please tell me, do you think we can compare this way? This infinite sum is convergent. Okay. If the sum exists as a finite number, it's convergent. What we can say about another sum that is greater? Can we also say that it's convergent? No. Yes, thank you. Yeah, thank you for typing this. Of course, no. Right? Because if this is finite number, something that is bigger could be finite number, but no, could be infinity. Okay? That means this is the thing that if you will have this formula, direct comparison test is not applicable. Okay? We can't use directly. Okay, but what mathematicians did, they still thinking this is a really good formula to compare. That means they developed a different way, okay, to compare, to use that formula. Okay, and I can show you. And we will call the other way, we will call a limit comparison test. Limit comparison test. And I have the summary on the next page, but I would like to ask you a few questions before I show you the summary. What we will do, you will compute for me a few limits. Let's take a few limits, of course, at infinity. Or I can even say x for now, okay? Like just let's do the function. What function I can ask you? Let's say x over e to the x, just the simple one. Do you think you can tell me the limit right away? Knowing which function grows faster, okay? Comparing the relative growing rates. Function x or e to the x grows faster? Yeah. Do you remember? Of course, e to the x, thank you, e to the x grows faster. That means if the denominator is winning, always is 0. And I can say, yeah, that's because of that relation. Of course, we can apply the L'Hopital rule. We have infinity over infinity, but now we know the answer right away. Okay, now let me limit as x goes to the infinity. Let's say maybe ln of x over, oh no, I want still, okay, let's say x squared over ln of x. I want this. Now, which function grows faster? Power function or logarithmic function? Yeah. Of course, the power function, x squared, thank you. That means x squared is winning, yeah, against the logarithmic. Logarithmic is increasing, but really slow. That means if the top is winning, oh, no. Oh, no, it's infinity, right? It's infinity. Okay. Now, what about this limit? Let's say 5x squared plus x minus 1 over 10x squared minus 6x, maybe plus 2. Do you think you can tell me that limit? Oh, it is 1? Okay, yes, I think I like the 1/2. Okay, at least both of you type the finite number, né? Not 0, I mean different than 0. Not 0, not infinity. Because now we have the ratio of two polynomials and we know that at infinity, we just investigating the leading functions. If the leading functions are the same, we just taking the ratio of the leading coefficients, which is, of course, 1/2. And now, if we getting a finite number, this means that both of the functions, and I can repeat them, this function and this function, of course, it's based on the leading terms, they kind of like behave the same, right? Because we didn't get 0. 0 indicates that denominator is faster. Infinity indicates that the top is faster. If we're getting a finite number, okay, different than 0, positive, of course, in this case, then we can say that both of them behaves the same. Okay, I can say this way, behaves the same. Okay, that means you probably, I think you're guessing what is the limit comparison. We will try to compute a limit at infinity, like I did, and we will take the original formula and we will divide by the new formula. My new formula that I figure out what I will compare with, it's the b sub n. This is b sub n, and my original one is a sub n. Okay, that means what we're doing, we will compute that limit, the ratio. Okay, and now, because we make a little bit easier for this class, that means what we're expecting, we only expecting a finite number, positive finite number, different than 0. Okay, I can say positive. Okay, we're expecting a positive number. Okay, and now what we know, if we will get from that ratio of the limit at infinity, if we get the positive finite number is something like here, 1/2. Okay, we know that the formula, the function, the expression a sub n, it's almost behaves the same like b sub n. Okay, that means this is extremely important conclusion. But now let's make one thing straight. If b sub n is convergent, then my original formula a sub n is also convergent. However, if b sub n is divergent, my original formula is also divergent. Because what is important, we're not looking at the relation. We're not looking, because direct comparison is not working. That means I'm not even looking at I do have two formulas, okay, and I'm trying to compare, and this is my new way. Okay, the only thing that I'm looking for is the limit with the positive finite number. If I'm getting this, I know, let's look at these functions. I know that both of them behaves the same. If this is divergent, this diverges. If this is convergent, this converges. Because they have to behave the same if we're getting a finite number. And this is actually the limit comparison test. Sometimes if you really like know, like if you really understand, you may make some conclusion if your limit is 0 or infinity. Okay, but then it's only for convergence or divergence. We usually say that if the limit is 0 or if the limit is infinity, we kind of we're not applying the limit comparison test. Okay, but you can still make some conclusion based on 0 and infinity. I can show you, but this is the main thing. And let's see, I did type for you. Okay, we do have to, we know what a sub n, b sub n means, and we're looking at that limit, that ratio. And if c is greater than, it's just the finite number, positive finite number. Then, because that's what I was trying to explain, because sometimes students are confusing, like, what do you mean both are convergent or divergent? No, we can conclude. Everything depends on the b sub n. If this is convergent, then both of them converges. If this is divergent, both of them diverges. Okay? That means that's the limit comparison test. If the direct doesn't work, please consider using a limit comparison test. And I type this for you But as I said, if you can pause the video and you can try to like digest this. Okay, let's say your limit is 0. Okay, if the limit is 0, you remember the limit is 0. It's telling me the denominator is winning. Or let me actually put the other way, because that's my original, that's my new one, and denominator is winning. Yeah, that's the only. That means how can I say? If you're getting 0 or infinity, then the inequality matters. Okay, for the finite number, inequality doesn't matter. Yeah, let's look at even here. Yeah, you can see I don't even have inequality. I say both of them are the same. Okay, that means let's see if we're getting 0. Okay, and then that's the conclusion. This means the denominator actually won. Then if this is the case, if B sub n is convergent, then I can conclude convergence, no problem. Yeah, by direct, I can even say direct comparison test. Or let's look at the infinity. If the limit is infinity, this means that the top function is winning. And then if my B sub n, the formula that I'm comparing with, it's divergent, everything what is bigger is divergent. And that's what we can say it's just not the typical, it's still good to use it, but this is the limit comparison test. And most of the time when we're getting 0 infinity, the students will say, oh, the limit comparison didn't work. Okay, because maybe the inequality was like, yeah, the convergence, divergence was like replaced. Okay? This will always work if you will get a finite number. Okay, that means you know the limit comparison and the direct comparison. Let's just do a few examples and we will be done. Okay, that means that's actually that's the formula that I was not able to use the direct comparison. Oh? That means what I will do, we know that it's good to compare with this one. Okay, and this is of course convergent. What was the relation? This way. That means direct comparison test doesn't work. Okay, I will try a limit. Oh, I don't need comparison test. Let's see. N goes to the infinity, a sub n over b sub n. Limit as n goes to the infinity. What is a sub n? It's my original one over this one. Oh, who can tell me that limit? This is this dividing by 1 over 2 to the n is multiplying by the reciprocal. You probably know the answer right away. 2 to the n, 2 to the n minus 1. The leading functions are the same, with the identical, not without even coefficient. 2 to the n over 2 to the n is 1. Okay, that means I got a finite, positive finite number. This means that the limit comparison works if b sub n was convergent, then I can conclude convergence. I mean, this works. I can say this converges by limit comparison test. Okay? And of course, we did compare with this one, but it's by the limit way. Okay. Determine whether the given series converges or diverges. Oh, similar formula, ln of n over n cubed. Oh, okay, I didn't. That's what I will do. I will take my formula and let me keep n cubed for now. And do you remember, we actually have two, we may put anything if we really know the relation, okay? But I will try maybe to put 1. Yes, do you remember? Ln, it's definitely bigger than 1, starting with 3. It's fine. That's not a problem. Okay, that means denominators are the same. numerators on the left, numerator on the left-hand side is greater. Okay, but now let's see what I really did. 1 of 3 doesn't matter. Do you think this infinite series is convergent or divergent? 1 over n cube. Who can tell me this? 1 over n cube. Of course, it's convergent, right? Convergent by P series test. Okay, and now that's the relation. That means, what do you think? Can I directly compare this way? That's convergent, finite number. Something what is greater, the summation could be actually anything. That means I can't really compare. Direct comparison test doesn't work with this. But you remember, we do have, that means now we can always make, that's the nice learning process. I can actually replace ln of n with n. N is greater than ln of n. Yeah, you remember I was drawing this, that's ln of n, that's just n. That means this is greater. Nice, because now the inequality, it's a little bit different. I can simplify nicely, and I do have 1 over n squared. Of course, this is convergent. Okay? Everything what is smaller, that summation will be smaller. Okay, must be convergent. That means it is my original, I would like to write somewhere. Converges by direct comparison test, but we comparing with 1 over n squared. Yeah, it's also really nice question for the multiple choice, because if you will see the answer convergent by direct comparison test and comparing with 1 over n cube, didn't work. I can even cross maybe everything. Yeah, this one, it's still good. Yeah, it's still good to go through this, but doesn't work. It is convergent by direct comparison test, and we comparing with 1 over n squared, because that was the thing. Okay, what else I have? Can you tell me what to compare with? I can maybe write a summation right away, because now we know. We should start, when we have logarithmic function, we always have to start with 3, because it's, okay, that means I can definitely compare ln of n with n, right? ln of n is definitely less than n. If the denominator is smaller, the whole fraction is bigger. And now we do have harmonic, divergent, everything what is bigger, it's also divergent by direct comparison test, and we comparing with 1 over n. Okay. Trigonometric are always fun, because we will do what I can do. I can keep 4 to the n, I can keep 1, but now can you tell me sine of n? What's the ratio for sine of n? Not the ratio, the range. How, like the sine curve has the maximum and minimum value? Yes, -1 and 1. That means you can see I can put 1, and then sine is always less or equal to. That's okay. Yeah, that means what I did, I only play with this sine of n, I replace with 1, and sine of n is always less than or equal to. Okay. And I think now I have nice geometric. Okay, let's simplify. I will have 2 and 4 to the n. just 4 in the denominator is taken to the power of n. That means this is my common ratio, or 1/4. Because 2 is just the constant. And geometric with the common ratio less than 1 is definitely convergent. Convergent, and it's the geometric one. The geometric series with the common ratio. Okay? That means now if I see the convergence, everything what is smaller is also convergent. Okay, convergent by direct comparison test, and now it's again really important to say 2/4 to the n. Okay, if this will be like, I don't know, 0, 1, it will not work. Must be exactly that formula. Okay, what else I have? Because I just want to, you can probably note the blue. I want to show you what to compare with, and then you can practice. And we can maybe skip this one. Or no, we can do it because I have this one. Oh, there, and I have multiple choice. Okay. Okay, let's try what we can compare with. Because we have to create a formula. Okay, n. And how e to the power of 1/n, how this behaves as a sequence. This is e to the power of 1, e to the power of 1/2, e to the power of 1/3, which is getting smaller and smaller, right? That means how this sequence behaves at infinity. Can you tell me, like, how I'm just trying to think what to compare with. That means if this starts with e, and then e to the power of 1/2, e to the power of 1/3, but can you tell me that limit at infinity? E to the power of 1/n. N is infinity. Of course, that's not a good notation. 1 huge number is a small number. E to the power of 0, it's 1. Okay? Also good limit to remember. That means we can see the terms at infinity, they're not gonna be lower than 1. That means I can say all of the terms are greater than 1. All of these terms of that sequence are greater than 1. Perfect. I do have divergence. Everything what is bigger, it's also divergent. Diverges by direct comparison test, and we comparing with 1/n. Okay, let's finish the session with this question. Do we know everything? Yes, I think we know all of, we have the whole knowledge. Okay, let's see if you will get some points on your midterm or on your weekly assignments. Consider the following series. The summation from 1 to infinity, 2 plus cosine of n over 9 to the n. Which of the following statement is true? Statement A, the series converges since the limit of this is 0. Do you think it's true? Please tell me the correct answer. I'm just A. Do you remember, if the limit of that sequence is 0, we know nothing. Nothing. Could be convergent, could be divergent. Yeah? If the limit is different than 0, that's the test for divergence. Then we can say that, oh, it's divergent right away. But that's not a good statement. Yeah? I can't conclude convergence just because of that limit, because the perfect example, actually, I can come back. Look at this. What is the limit at infinity of 1/n? Of course, it's 0. And actually, the series is divergent. Okay, that we have to be really careful. That's not a true. Okay, the series is geometric series. I see 9 to the n placed in the exponent, but I also see n somewhere else. That means it's not direct. We can compare with geometric, but it's not geometric on itself. No. Okay. Now we do have some. Okay, let's see. Converges by the limit comparison test, and it's comparing with this. Converges by direct comparison test. Yes, I think, yeah, okay, I see the answer. Okay, because of course we have to be really careful, right? But only one answer is correct. Okay, the thing that limit, okay, what I will like, how I'm thinking. When I see the trigonometric part, cosine, sine especially, and the limit, we know that limit at infinity of, let's say, cosine of n. Can you tell me this limit? Or the same for sine? How function cosine and sine behaves at infinity? It's like +1, -1, +1, -1. I mean, we don't even have to write like, I mean, the limit simply does not exist. Not always, because depends on the other part of the formula. If they, like, we may use this, we can still compute some limits. Yeah, we can use some squeeze theorem, or we can definitely get something, but sometimes we can think that no, the limit when the trigonometric function is undefined. Okay, I mean, in this case we can still compute limit. You can see this, because this is just positive -1 plus 2, it's still like a positive number over huge number. If the denominator is winning, of course it's 0, but we can always think about this. Okay, that's what I will do. I will not even reading the options. I will try to actually solve the problem, not seeing the option. And I just got a hint from you, from Roger, that we can keep this. And we remember cosine of n, it's always less or equal to 1. Okay, and now you can see we do have 3/9 to the n. Just 1/9 is taken to the power of n. That means this is the common ratio, less than 1. This is the geometric convergent. Okay, if it's convergent, everything what is smaller, it's convergent. That means I think looks like that. And since I see convergence, then I will eliminate this right away, because we can still think, but it's not doesn't diverge. And this one, just to be sure, let's actually see how the limit looks like. Yeah? Just to show you that doesn't work. If they want to apply the limit comparison, I have to take my original formula and divide by the new one. Because original one is 2 plus cosine of n over 9 to the n, and the new one, they just set 1/9 to the n. Let's simplify. 2 plus cosine of n over 9 to the n, 9 to the n over 1. I just flip. Of course, this is gone. And actually, yes, that's what I was saying. We just end up with 2 plus cosine of n. And since cosine at infinity is like +1, -1, +1, the answer will be 2 plus 1, it's 3. 2 minus 1, it's 1. Of course, we can't say like that. We're just saying that the limit simply is undefined. Okay? We can't really use that. We do have a proof. Okay? Just I want to show you. Okay, I will switch off my camera. I'm still there. That means please practice a lot. I think for each section, when you check the summary notes, I put like a list of problems, and I also solved for you. Okay? Of course, I will still put the practice with Kasia videos, but please solve any like formulas, any series. Okay, apply, of course, the tests. Okay, we have to highlight the comparisons now. Okay, and I'm sure you will be good, but please practice a lot, because what we do have a spring break, right, next week. That means I hope you will not forget everything. And then after the spring break, you will come back and we will still have a new test. Yeah, you see the bottom of the page. We still have a new test. And then after that week, we will have a midterm. Right? And the midterm test, midterm 2, it's almost everything about the infinite sequences and series. Okay, thank you very much for today. Thank you.